Hey everyone, let's talk about Python. And in this lecture, we'll go through a fairly detailed analysis project from start to finish that'll, I think, do a good job of showcasing both the power of Python in collecting and analyzing financial data, as well as underscore some of the common pitfalls that you'll actually bump into once you start looking at and working with real financial data. So in this example, our objective will be to get the factor exposures and idiosyncratic risk of a common stock, let's say Apple. Obviously, this is going to be an important thing for investors, portfolio managers, as well as analysts to consider. This is the sort of problem that gets solved every day, and here is how you'd go about solving it using Python. So first you're going to need to figure out a way to collect some data. And a good way to do this in Python is to use the pandas data reader. So as you know, to include a package, you simply say import, and in this case we'll be adding pandas data reader, which is a package that has connections to many financial data sets. We'll in fact see just how many quite shortly, which we'll be using some of to collect the data that we need. Of course, if we want to collect the factor exposures of a certain risk asset, let's say a stock, we're going to need the time series of the stock's returns, as well as the time series of the factor returns we want to consider. And perhaps also we will import a plotting tool. A common one in Python is matplotlib. And we'll give it an alias just to make things shorter so we don't have to type out matplotlib.pyplot each time we want to use it. We'll give it an alias of plt. So the good news about Colab is that common Python packages are actually included already, so you don't have to do any installs. Import just says, all right, you already know about this package, now load it up for me into this program so that I can use it. Now that we've got these two in, let's actually see what we can get out of pandas data reader. So if we type pandas data reader, if we wanted to make our lives a bit easier, we could have given that one an alias as well. But let's say we just type it out. We can look at, as you can see here in the autocomplete, several different possible data sources. The one that we're going to be interested in is Fama French, which gets data from Ken French's online research library, which contains the returns of common risk factors. And then a method that we can use, and as you can see the autocomplete already picks up on it, is the getAvailableDatasets method. So if we run that, this will tell pandas data reader to go to the Fama French site and tell us what sorts of data we can actually get out of it. So let's execute the cell. And here is what we see. There's actually a tremendous number of various risk factor portfolios. But the one we're going to be most interested in is this Fama French research data factors. Of course, this is based on the Fama French 3-factor model. But what if we want to go a bit beyond that? Well, we can also add the momentum factor. You'll see it in this list right here. We'll just have to include it separately. But now we know that we can get both of these factors, or groups of factors, into pandas data reader. So to actually get them, first we have to give it a start date. In other words, starting when do we want these factors? Let's for now go as far back as we can. If you've used these factors before, you'll know that they're maintained since 1926. So let's create a new variable called start, and we'll set it equal to the date of January 1st, 1926. Now, let's actually then use Pandas data reader combined with the start date to get the Fama French 3 factors since 1926 onward. So let's say we're going to have a new data frame. We'll call it FF for Fama French, and we'll assign to it the output of Pandas data reader. It's Fama French data, which we'll need to access using this Fama French reader method. And now that we know what we want to pull out from this list that we just viewed above, we can actually type it in. If you recall, or if you want to just loop back a bit in the video, the Fama French 3-factor data was called FF research data factors. Now that'll tell us what we want. We also need to specify how frequently we want it. So as you can see, there's the frequency field in autocomplete, and we can give it the character M for monthly. We could also do D for daily. But one sort of bit of research wisdom is that daily factor returns are far too noisy, so you're less likely to get a good measure of factor sensitivities, and it's generally easier to do so if you measure returns both on the risk asset and on the risk factors at the monthly scale. And finally, we'll deploy our start date, which is going to be 1926 January. And then if we just tell it to read this, it appears to have done so, but let's confirm it by actually just typing in the name of this new data frame we created to have Python display the data frame. Actually, we see that this isn't exactly a data frame. There's two things in here. Element 0 is indeed the data frame, and element 1 is something else. So actually, let's just get the data frame of returns by taking the first element of this thing that the Pandas data reader spat back to us, containing these two elements. The first element was the actual data frame of factor returns, as you can see, 1,140 rows, 4 columns for each of the 3 factors plus the risk-free rate. And the second one was 94 rows and 4 columns, containing just the annual versions of them, it seems. Whatever it is, we don't really want it. The other trick, of course, in Python is that it's 0 indexed, so to get the first element of anything, you actually get the 0th element. So this new data frame FFDF is going to have the daily returns, sorry, the monthly returns, for each of the factors as we desired. Now, Pandas actually will let us plot the elements in this data frame, so let's just have it do that. So we'll call the data frame, and let's plot not the actual returns. Well, actually, let's plot the actual returns themselves first. We'll see maybe if there's a more easily visualizable thing that we could do after that. Let's plot them by themselves. So each series in a data frame by itself. And let's specify a size for the figure. Okay, we see that, yes, the data series do seem to be there. The problem is that they are fairly noisy. It's a pretty squiggly line. So let's see what we can do to smooth it out. And this, I think, does a great job of illustrating some of the power of pandas in manipulating data series. So let's say that instead of plotting these figures the way that we just did, let's say we'll plot the smooth moving averages of it. So for that, we'll use the rolling method of pandas. Let's say a 72-month rolling window. Over this 72-month rolling window, we'll take an average. And now let's plot that. As you can see, that smooths out a lot of the squiggles, giving us a much better view into what the factor dynamics are. So we can see, for example, that the market factor and the size factor took a dip in the late 70s, and later they've been actually moving inverse to each other, and size and value have sort of been moving together with each other more of late, whereas they were moving opposite to each other more in the middle. These are the sorts of insights that you could draw much clearer if you're looking at rolling averages rather than just sort of the month-to-month fluctuations. But this just confirms to us that the data series are there and they look sensible. So now let's also add to this the momentum factor. So since we now know that Pandas data reader is going to give us this list effectively of two elements, only the first of which we want, we can actually combine a couple of the commands that we just executed to get the data frame with the momentum factor a bit faster. So let's first say what we're going to want to call it. Let's say we'll call it the Fama French momentum data frame. And again, let's do Pandas data reader, Fama French reader. And in this case, remember the other item that we spotted in the list of series that were downloadable was the FF momentum factor. And again, of course, to make things make sense, we're going to want this at the same frequency as the rest of the factors, and with a start equal to the start of the other series. We're going to want to use that same read method to get it, but now we can actually just save a step and already grab the first element because we know the second element is not what we want, and it's going to give us both unless we specify. And just so that we're sure, let's actually plot the 72-month moving average of this data frame. Of course, this data frame has only one series because there's only one momentum factor, but we do see that now it is there. Now, this does mean that we've got a bit of a problem, and this sort of brings us to the first of the data challenges in running a financial analysis project. We've got a data frame of 3 risk factors, another data frame of 1 risk factor. How do we actually combine it into one data frame with 4 risk factors? Well, the good news is that Pandas has a merge method, so we're going to want to merge them. And we're probably going to be able to do it on a common identifier. Obviously, when you merge, you have to have some way of connecting two data sets. In this case, we can probably do it by date. Let's actually just take another look at FFDF. We see that indeed the date is monthly, so we start in July 1926. What about the momentum data frame? Well, it starts a bit later, but it looks very much the same. It's still monthly, and it looks like the date identifier is indeed going to let us map one to the other. So let's see if we can make that happen. Let's say that we're going to want to create a new data frame called a fac merged df. And what we'll do is we're going to call the merge method of pandas. And to do this, we're going to need to, of course, specify what data frame we want to merge to what data frame and on what. So let's merge our Fama French 3-factor data frame to the Fama French momentum data frame. Now, how do we want to merge it? This gets into sort of the way that you think about relational databases. You can do inner joins, outer joins, left joins, right joins. In this case, since we have literally the same identifiers, which are monthly dates, let's just do an inner merge, which means that we're only going to take observations from both data frames and connect them one to the other in the cases where the dates match. So in this case, I guess our resulting data frame should start on January 1927, because that's the earliest date that exists in both, and any date that exists in both will be part of our final result. Let's just say that we're going to also want to sort the output. Let's say that we'll make a copy. Let's say that we don't need an indicator, which would otherwise tell us was this particular observation included in the first data frame and the second data frame and both and neither. We don't really need that. But one other data science trick that we probably can use is the validation statement, where we can just say what we expect the merge to be like, and then Python will tell us whether it actually was. So in this case, we expect this to be a one-to-one merge. In other words, we don't expect a date to occur more than once in either of the two data frames. And if it does, Python will complain, and this statement will then let us know that something was wrong in our data setup. Oh, and of course I forgot to import pandas itself. In other words, pandas is already included, but it wasn't included as this alias PD. Oh, and I think the other thing we forgot is actually what we want to merge on. In this case, we know that the common identifier is date. Well, that seems to have gone through. Let's see how it actually did. Well, that looks pretty good. So indeed, the data frame now starts in January 1927. It does have all 4 of the risk factors plus the risk-free rate. And it goes until June 2021. As you can see, these are the factor returns. It looks like they're in units of percent. That's all pretty good. So it looks like our risk factor data is pretty much set up. Now let's think about how to get the data of the risk asset that we actually want to regress on these risk factors. All right, so let's say we want to get data for Apple as our risk asset. So let's create a new data frame. Let's call it Apple DF. And let's pull in data from Pandas data reader here. Now, of course, Apple isn't a Fama French risk factor, so we're going to have to look at a different database to try to get this data. So where can we look? Well, we can go to Yahoo Finance. So the get data Yahoo method grabs data of Yahoo Finance, which of course has individual equity return data. So to get this, we're going to want to specify what ticker we want. In this case, we want data for Apple. Let's say that we want to start at the same time. Of course, Apple didn't exist back in 1926, but if the actual start date is after, then it will give us data sort of as far back as it can. We could also specify an end date, but if we don't, we'll just get data up until the most recent observations, as we did with the Fama French factors. Now, unlike the Fama French stuff, of course, price series for equities have different fields. You've got the open, high, low, close, and importantly, actually the adjusted close, given that Apple's actually done some corporate actions that would have changed its price just based on how many splits they had. So let's say we're going to pull in the adjusted close price of Apple. Now also we're going to need to think about how frequently we want to get it. Let's say that we want monthly to align with our data frequency for the risk factors. And let's say we want, of course, a contiguous series, and also, importantly, since we're getting close prices, that means that we want, if we want to compare the returns on Apple to the returns on the risk factors, we're going to actually want returns. Fortunately, Pandas has a percent change method that will actually compute returns. So that looks pretty good. Let's see what happens if we run it. Well, here it looks like what Python is complaining about is actually it can't seem to access this data set. And unfortunately, this is another common data issue that you will face if you work with financial data, is that sometimes the technology will change in some way, either on the database's end, as is the case here, or in some other way. So in this case, actually just calling Pandas data reader simply won't work. So what do? Well, thankfully there's a workaround, and it involves updating and overriding the original Pandas data reader with sort of a fix. Now the bad news is that this fix does not exist in Google Colab, so we actually have to take a detour to the Python package manager to actually install it. Remember, we can import things that have already been installed, but we first have to install things that haven't yet been installed before we can import them. And in this case, what we want is a package called Yahoo Finance, which is a Yahoo Finance fix for Pandas data reader. Now, how do we actually access pip? Like so. And we can say pip install whatever the name of the package is. In this case, our package is Yahoo Finance. And thankfully, Colab is flexible enough to let you install your own packages, just like this. Now, I'm not sure if the LXML issue is going to cause us any problems. Let's see what will happen if we actually try to use it. Specifically, what we want is first we want to import Yahoo Finance. And second of all, we want to actually use its method instead of the one built into Pandas data reader to access Yahoo Finance. So let's see if this works. Well, that doesn't seem to be bothered by this LXML issue, but now let's see if the command we were actually trying to run, which is to download data for Apple from Yahoo Finance, if this will now work. Well, that doesn't seem to. So let's do as it suggests. Let's restart runtime. In other words, this is going to be analogous to going to runtime and saying restart and run all. So far so good. We were able to collect our Fama French merged risk factors again, but of course we lost the connection to Yahoo Finance again because we lost our import of Yahoo Finance. So let's try installing Yahoo Finance again. Let's try importing it. And now let's run the command to download Apple's data again with the important correction that we needed to add the data method to get data Yahoo correctly. But now that we have changed the way that Pandas data reader works using this Yahoo Finance package, we should now be able to get Apple's data, and so it seems that we have. Now, what did we actually get? It looks like we've got a series of data. Let's actually get a data frame. And now we should think about how we want to merge this with the data frame of our risk factors, because ultimately we may want to get everything into the same data frame just so that it's easier to line things up. Now we could of course specify the data from separate data frames into a regression model, but we'd still better have the same number of observations in both our y vector, which is to say Apple returns, and our x matrix, which is to say the risk factor returns. We see that right now that's definitely not going to be the case because the Apple series starts in 1980. Our risk factor series starts back in 1927. And, well, we might want to hedge against the possibility that some month is missing somewhere. So it's easier first to just make sure that everything is merged, the dates are unique, and then run a regression on that single data frame. Now the other thing is that if you look, our date index looks a little different. In other words, we see not just the year and the month, but also the day for Apple, whereas for our risk factors, we just see the year and the month. So let's look into this a bit more deeply. Let's actually say what the data type of our index in each frame is. So index is just this first column. And for Apple DF, the index data type is a timestamp. Well, that's pretty good. However, what was it for our risk factors? Now we see that here it's a period. Well, the period of the month over which that factor return was observed. Now this is going to cause us problems because if you have different data types, you can't actually merge two databases even if they look otherwise the same. And of course here we know the dates aren't even going to be the same because one of them includes days, the other doesn't. So to do this, we're going to have to change the index on both data frames, which leads us to yet another data challenge. We have to actually re-index both data frames, give them an index that is mutually comparable, and then perform this final merge, adding the Apple data frame to the risk factor data frame. Now, changing the index of a data frame in itself is actually not straightforward. You can't just change its data type immediately. So let's sort of do a workaround. Let's create an intermediate value, which is going to be the string date, a new column in the data frame. And that'll be the value of the current index that we're using, that we're going to cast, in other words, change type of, into a string. Now you might wonder why we'd want to do that. In other words, what would this accomplish for us? Well, what we're then going to do is we're going to modify this string, and then we're going to do the same in the other data frame, and we'll end up with a variable that is actually formatted the same way in both data frames. So before we execute the cell, let's do another step. Where we're going to create a new column yet, which is going to be a date version of this string. So the toDateTime method of pandas will actually create a date from a string. In this case, of course, the string that we want to create the date from is the one that we pulled out our index. And now if we give it from datetime the strftime method, we format it as a year month string, that'll give us a date that has year month only. And if we do the same thing in the other data frame, that'll give us a date identifier that actually has a common format across both data frames. And just to make sure that we have done this, let's actually see what the data type of this new dtDate variable that we created is. You can also access a series in a data frame by just typing out its name. You don't necessarily have to do the square bracket string name. So dt.date and apple.df. Let's see what its data type is. Okay, it's an object, it's a string. Well, now let's do the same thing for our risk factor database. So we're going to take the index of our risk factor database, we're going to again convert it to string. We're going to create a string date variable in our risk factor data frame. And then we're going to convert this string variable into a year month date string only. So if that sounds confusing, remember the basic idea is we just want dates that are formatted exactly the same way in both data frames. They don't even have to be the index. There just has to be a variable that looks exactly the same so that the matching algorithm can actually find a common identifier to merge the two data frames on. And let's actually also check the data type of this identifier that we've created. Of course, it's going to be a string, so in that way it won't tell us that much directly, but at the very least we're now closer. We know it's a string, it's formatted year month, so we're definitely going to be more likely to find a mutual match than if we were looking at timestamps in one data frame and periods in another. But, of course, the proof of the pudding is in the eating, and the proof of unique common identifiers is in the merging. So let's actually perform a merge. So let's create a new data frame that's going to be the merge of Apple and the Fama French risk factors. Now we've seen the syntax before. We're going to use the merge command from pandas. We're going to merge on, or we're going to merge the Apple data frame and the risk factor merged data frame. Now we're going to merge it again as an inner join, because we want to make sure that we're only capturing observations that have the same monthly value. We're probably going to want to tell it on what we want to merge it on. So remember, we created this DT date string that should be year month formatted, that should be the same in both data frames, so that's the one we want to use. Let's say we again want to do sort true, copy true, merge indicator false, validate. Yes, let's actually do that. That'll be important here, because we really want to be sure that we aren't getting anything weird with these string dates that we created. Well, that seems to have worked. Let's actually see what we ended up with. So let's just call the name of this data frame and have Python tell us what it looks like. Well, and it looks pretty good. It looks like we probably should give Apple's returns, because remember we did %change, so we got changes in Apple's monthly price. So it's not really the adjusted close, but we should give it a more elegant name, probably something like Apple. But we do have duplicates in that string date intermediate variable. There's one in the first data frame and one from the second data frame that was merged. The good news is you can see that the DT date variable was indeed identical, and it was indeed just year month in both data frames. So really all we need to do is just drop this str date that we got from the two data frames separately. We no longer need that intermediate step, and we should probably rename adjusted close to something more elegant like Apple. So let's do the first bit. Let's actually drop those two columns that we no longer need. So we can use the drop method from a data frame. We're going to want to tell it that we want to drop certain columns, which are going to be str date x and str date y. And we also want to just do this with the data frame without copying it over to another data frame, so we can say in place equals true to get this to happen to the data frame itself. Of course, the other way to do it would be to assign the result to a new data frame. So that's good. Now the other thing that we wanted to do was rename edge close to APL. So for that we can use the rename method. And here again we're going to want to specify which columns we want to change, except in this case we want to give it a dictionary effectively. I want to say what used to be called edge close is now going to be called APL. And again, we want to say that instead of copying this to a new data frame, let's just change the current one. So in place equals true. Now let's see how that looks. Much better. Now the other thing, of course, is if you look at the magnitudes of our returns, you can clearly see that the risk factors are in percent, whereas the apples returns are just in decimals. So we're probably going to want to convert apples returns to the same units so that we can run a sensible regression. And as you probably know, for risk factor models, we also want to subtract the risk-free rate. So let's do both in one fell swoop. So let's actually say that we're going to create a new column, which will be APLRF, in other words, apple net of the risk-free rate, and that will be the APL column times 100 to convert the decimals into percent, minus the risk-free rate returned for that same period. And this is, of course, another reason why we probably needed to merge these two data frames together rather than have Apple in its own data frame and the risk factors in their own data frame. We just need to have at least the risk-free rate next to the Apple data so that we can properly difference the returns to our risk asset and get the excess returns to get the risk factor model to make economic sense, because risk factor exposures give you risk premia in excess of the risk-free rate. So if we run that, we can actually rerun this cell to see how our result changed. We see we have now this new column. It's in the same units as our risk factors, and it is now indeed Apple's returns net of the risk-free rate. Now the last thing that might bother us a bit is these NANs. Now remember, if you want to run a regression in a more user-friendly environment, maybe in Stata or something, you don't have to worry about missing values. It's sort of equipped to deal with them. If you want to run a regression in Python, you're much better off getting rid of missing values yourself rather than risk finding out how the particular API you're referencing is going to deal with it, if it will deal with it at all. So let's actually use this command drop NA on rows to drop any row that has a missing or NAN value in it. And now we see that that indeed has been done. However, we see that this was not done in place. So if we forget the in place equals true statement, then that means that our change won't actually be saved. Now that we remembered it, it was. This data frame now should not have missing values. So good. This is actually a pretty big accomplishment. As they often say in data science, about 80–90% of your work is actually cleaning data. And if you think about what we've been trying to work toward, which is to run a multivariate regression of the returns of one risk asset on a factor model with 4 risk factors, just now, after all this time, we're actually in a position to do it. So let's use stats models in Python. It's a more user-friendly version of regression. You can also use scikit-learn, but you won't get nearly as useful output. And here we just want to look at factor exposures. So let's look at stats models. And from it, what we want to get is just the ordinary least squares, or OLS, model. And what we want to do is we want to get the results of our regression. We want to save them to a variable, which we'll conveniently call results. But what is our model setup actually going to be? Well, the OLS method of stats models has us first say what our y value is. And of course, our y, well, vector, is a PLRF. That's our dependent variable. We're going to want to regress that on our 4 independent variables. Which are the 4 risk factors. Now for this, we're going to want to actually specify a list then. So from our Apple Fama French factor merge data frame, we want several x values. Remember, you can only have a single y value, or well, a single y vector, but you can have an x matrix. And here, that is exactly what we're going to do. The first series we want is the market RF risk factor, in other words, market in excess of the risk-free rate. The next one is going to be the small minus big risk factor, aka the size factor. The next one is going to be HML, the value factor. And the last one is going to be MOM. That's going to be our X matrix, our independent variables. Now what we're going to want to do, just in case, is if there's any other missing values, let's drop them. And let's actually fit this model. Now, that doesn't sound good. It says that momentum, MOM, is not in this data frame. But if we scroll up, we see that it most definitely is. APL, fact merge df, here is MOM, capital M, lowercase om, and that is indeed how we are trying to access it here. Well, first let's see what would happen if we got rid of it. Would the rest of it work? Well, the rest of it seems to work, but before we look at those results, let's see why this appears to be breaking. Now let's also put in the right string delimiters. So why is MOM not a column that we can find? Well, let's actually list what columns there are in this data frame. Okay, and that pretty quickly tells us what's going on. As you can see, the rest of these are just as we were writing them, except for MOM, which for some reason has 3 spaces behind it. Why? Well, don't ask me why, but the good news is that we can do this or get around this in a couple different ways. First, we could probably just put in 3 spaces in its name. See if that works. Well, that works, but that's a bit weird looking, so maybe it'll be easier if we just rename MOM to something without those spaces. Good news is we know how to rename columns in data frames. So let's say that in this data frame we're going to rename m lowercase om space to, let's just make it consistent with all the other risk factors. Let's make it an uppercase MOM. And remember, we have to do this as an in-place rename. Otherwise our change won't actually be saved to this data frame. Now let's see what our data frame looks like. Remember, the cells in a notebook can be run effectively in any order. So whatever change was made is now going to be reflected even if we run an earlier cell. So indeed now we see that MOM has a more sensible name. And now if we call it like so, that does seem to work. Let's actually maybe just reorder our cells a bit so that they are more sensible in a chronological order. That way, if we do rerun the whole notebook from start to finish, we will have made the proper rename to MOM, and then we'll get the stats models OLS estimator to run without all of this hullabaloo that we just went through. So now that we actually have regression results, let's actually see what they look like. Well, that looks reasonably good. We've got coefficients for the risk factors. We've got t-stats for the factors. If we want to know about idiosyncratic risk, in other words, the part of Apple's returns that is not explained by the risk model, we've got an R-square. One thing that sort of troubles a financial economist with attention to detail would be the fact that we don't have an intercept. Remember, a factor model actually should have an intercept, which is to say an alpha. The good news is that we can fix this also, so let's just do that. For this, we'll need to add another thing from stats models. Actually, we can just write it this way: import stats models dot tools. And from tools, what we're going to want to do is let's actually create a new version of our factor data frame with our risk asset that also includes a constant. Again, more like let's say user-friendly or less programming type and more like stats user interface type languages. We'll just throw in a constant for you. But Python does not. So unless you actually give it a column of ones, it is not going to include a constant in your OLS model. So let's give it a column of ones, and that's what the stats models tools package will actually do for us. So we'll have this new data frame. It'll have a constant in it. That's why we added the _c, just to denote it from as different from our earlier data frame that didn't have it. And so now let's say statsmodels.tools .add constant. So this is the method that was developed precisely to correct for this issue. If you want to add that column of ones to your data frame so that you can run a regression with an intercept, this is how you can do it. So you have to tell it what data frame you want to add it to. In our case, it's this data frame. And let's say we want to prepend it. And now let's see what we have ended up with. And indeed now we see that the first column in our data frame is one called const, and it is indeed a column of just ones. It may look a little silly, but mathematically that's what you have to have in your X matrix if you want to run a regression with an intercept. So now let's go back to our OLS estimator command. And now we can add const to our list of X matrix columns. And let's also say results.summary. So now we can estimate a regression of Apple's returns on an alpha plus exposures to each of the 4 risk factors: the market factor, the size factor, the value factor, and the momentum factor, at monthly frequency. And we can actually see its loadings as well as its idiosyncratic, sort of unexplained portion of return variability. Oh, of course, to actually get that to work, we need to use our new data frame. Because remember, our APLFAC merge DF data frame didn't have the constant in it. The one that ends in _C does. So that re-emphasizes the importance of keeping track of your namespace. And now we do indeed see that we have an alpha, as a proper factor model should. In fact, we see that for Apple, this alpha is positive and highly significant, about 1.4% per month. We see that it has a significant exposure, a beta of about 1.2 on the market. It has an insignificant exposure to value. It has an insignificant exposure to size. It has a negative significant exposure to value, which makes sense since Apple is a growth stock. And interestingly, it has a insignificant exposure to momentum. And overall, we explain about 28% of the variability in Apple's returns, suggesting that there's actually a fairly big idiosyncratic component. So this is sort of the process from start to finish. As you can see, there's quite a few takeaways. First of all, the data cleaning part is going to be a large, perhaps very large portion of the total work that you do on a data project. Getting it to the point where you have a clean data frame that looks like this last one that we created took us most of the time that we spent together. There's also going to be weird data things like our inability to access Yahoo Finance before we implemented the workaround. There's weirdness in formatting across data frames that we had to fix with this new date variable that we created from the index of the 2 factor return data frames. There was a bit of weirdness with the way that the momentum column name turned out. there's always going to be errors. There's hardly ever going to be a project that you just start and get to the finish of without running into some truly inexplicable things that you have to spend some time puzzling over. But I hope this gives you sort of a good flavor of both the promise and the peril, in a way, of data work in Python. It's very powerful. You can access very many different data sources within Python itself without having to go and download data sets. Of course, it's very powerful in terms of the analysis that you can conduct. OLS is just perhaps one of the simplest types of data models that you can actually run in Python. It can run all sorts of more sophisticated linear models as well as nonlinear ones. But also you sort of see some of the rougher features in terms of getting data to merge correctly, in terms of accessing data, accessing individual columns, all of these sorts of nitty-gritty details that really make up the core of data work. Thanks for listening.